G'day, in this video we're going to be applying magnetic fields to charged particles and looking at how that can be a little bit different to applying an electric field to a charged particle. So we're still looking at dot point 6.1, that first inquiry question, what happens to stationary moving charged particles when they interact with an electric or magnetic field. We're looking at introducing dot points 3 and 4, which focus on that magnetic field aspect of the inquiry question. We're going to be introducing a new equation that looks at the force applied on a charged object when it's placed in a magnetic field B. And by unpacking that and a few other concepts a little bit further, that's going to allow us to start to compare the behavior of charged particles in different fields. So our key learning intentions is to start to look at how we can calculate the magnitude of forces applied to moving charged particles when they move through a magnetic field. Apply the right-hand rule to determine the direction that a force is being applied on that charged object, and then begin to explore the motion of particles based on the angle between the velocity and field vectors, and apply mechanics equations where appropriate to describe that motion. Let's have a look first at this new equation, which is that F is equal to QVB sine theta, or F is equal to QV perpendicular B. What's being said here is that the force which is being applied on a charged object due to a magnetic field depends on the amount of charge that the object has, the velocity that the charged particle has as it moves through the magnetic field, and the strength of the magnetic field itself. Then we also have this theta variable which describes the angle between the velocity vector and the vector of the field line. In a scenario where sine theta is equal to 90, you don't have to substitute anything in because sine 90 is equal to 1. Thus, if the velocity vector is perpendicular directly with the magnetic field, then it's just, QVB. That equation should be quite simple and straightforward to apply, and we will do so as we practice with it in class. What I do want to highlight for the moment, though, is the right-hand rule that we use to determine not just the magnitude, but the direction of the force experienced by the charged particle. So sometimes you'll see right-hand rules that look a little bit like this. I do prefer the one where you stick out your 3 fingers because I think it makes it really clear where each of the 3 axes actually are. So just like we've seen with other right-hand rules, what we have here are 3 vectors which are all perpendicular to each other. And by holding your hand in this shape, you can see the direction of the magnetic field lines. That would be your middle finger. You can see the direction of the velocity of the charged particle. That would be your index finger. And thus the resulting force points upwards with the thumb. Keep in mind though, and this is also really important to consider, as always, the force that's being shown, the vector that's being shown, reflects the behavior of a positively charged particle. So if you were to have a positive and negatively charged particle moving through a magnetic field that's pointing in this direction, and the object's moving this way along this axis, then the positively charged particle will experience a force that makes it move upwards, and the negatively charged particle will experience a force which makes it move downwards. Now, depending on the angle that you have between the velocity and magnetic field vectors, will significantly influence the type of motion that the particle has. Interestingly, if the particle moves in the same direction as the magnetic field, there is no force that is applied by the magnetic field onto the charged particle, which means that both vectors remain parallel, that there will be no change in the velocity effectively. If you have perfectly perpendicular velocity and magnetic field, what you will then have is a constant force that's being applied perpendicular to both of those, and it actually results in circular motion like we've seen before in Module 5. We will unpack this further in class, but I want you to appreciate that this force that's being experienced will be constant because you're not actually changing the magnitude of the velocity here, you're just changing the direction. What I want you to appreciate is that if you move in this arc motion, the direction of the velocity vector will continue to bend inwards more and more and more. And because the velocity vector has to be perpendicular to the force vector is also going to change its angle as well. And what this results in is the force vector always pointing in towards this central point of a circular arc. Effectively, what this means is that the force caused by the magnetic field on this charged particle acts as a centripetal force, which then gives uniform circular motion. Again, something that we will dig in a little bit deeper on in class and unpack with some practice problems. So what happens if you have the charged object not moving parallel or perpendicular to the magnetic field, and there's some other weird angle between 0 and 90 degrees that sort of shows this motion? Well, you do still get some sort of circular shape that's happening, but you will still have the charged particle moving along the magnetic field rather than just moving in a single circle, and you end up with a helical path or some sort of spiral. Thank you very much, everyone. In the next video, we'll start looking at ways that we can produce magnetic fields from an electrical current, and this is going to really help us to dive into the rest of the module and all of its components. But until then, have a good one.